Till now, we have seen that for solid to solid phase transformation, delta G is given as minus 4 by 3 pi r cube delta G V minus delta G epsilon plus 4 pi r square gamma alpha beta we call it. Please correct if I have somewhere by mistake wrote SL. So this is the free energy of formation equation, and then we got the equation of R star 2 gamma alpha beta by delta GV minus delta GE. We also got the equation of delta G star is 16 by 3 pi gamma alpha beta cube by delta G V minus delta G E square. So, and then we have seen that in presence of this term, the free energy, critical free energy as well as the critical nucleus size both increases, so it becomes very difficult to nucleate a different phase into solid phase material. But we have not, till now we have not explained what is this delta G term. So delta G term, we know that this is elastic strain energy per unit volume. This is elastic strain energy per unit volume. If you see different books, you will find different relationships, which describe this equation, this term. So delta GE is given as CK epsilon square. So CK are constant. C essentially represents composition. Actually, composition difference. A is a Bach modulus. And E is strain. So this is how generally, in a very simple manner, it is defined. This free energy term. If you see this is modulus, it will have a unit of MPa. It is like nothing but Newton per meter square. The unit will be Newton per meter square. You can write Newton meter per meter cube. So Joule per meter cube. So this is how it is energy per unit volume. So elastic strain energy per unit volume. But if you want to be more specific, this term is very complex, but there are some general derivations given in different books. But there is a book called Kinetics of Materials by Carter and his other co-authors. So you can follow that book if you want to see all the details. But now the question is, suppose this is the crystal structure of alpha phase. And in the bottom you have, this is just here what is shown is the just boundary. So in the above you have alpha phase, below you have the beta phase. So when alpha and beta, two phases, they coexist, you can consider the beta phase. You can consider the beta phase to be an implosion inside the alpha phase. So the beta phase can have different shapes. So what kind of shape it will take? the system will actually, the whole material will try to reduce the overall energy. In order to reduce the overall energy, it will achieve a shape which is most favorable. But there can be disc-like shape, there can be needle-like shape, there can be spherical shapes. Actually, if you see material, we often encounter different shapes of inclusions, different shapes of different phases. Those are mainly governed by this energy balance. So anyway, now suppose you have beta phase inside alpha phase, so there will be a boundary between these two phases. Now, if you consider this boundary, alpha and beta, there will be variation in lattice parameter. This. So what happens if you see, so you have atom here, here. So it is like you have continuity in the lattice structure, but the structure is little bit distorted. So this kind of boundary, and this is the green boundaries between this alpha and beta phase. These two different grids. So this, when the continuity is maintained along the boundaries, the continuity of the lattice structure is maintained along the boundary. This kind of boundary is called coherent. Coherent boundary. But suppose during this nucleation of beta phase, if the volume change is too high, what will happen? Along these boundaries there will be some slip, some shear deformation, and some of these boundaries will be broken, and then it will be called semi-coherent. If all the boundaries are broken, there will be of course this attractive or repulsive forces, there will be atomic bonding, but I mean the broken means the continuity of the lattice structure is not maintained. So when the continuity is maintained, then it is called coherent boundaries. If the continuity is not maintained, then it is called non-coherent. Non-coherent. So similarly, you can have semi-coherent. Semi-coherent and boundary. So there can be different types of boundaries, and depending on these types of boundaries, whether it is coherent or semi-coherent or non-coherent, the elastic strain energy will vary. So moreover, the elastic strain energy will depend on the stiffness of alpha phase as well as the stiffness of the beta phase. If they are similar, then this will be called homogeneous system or homogeneous boundary. If not, then this will be called non-homogeneous. So we have just discussed that if the continuity of this crystal structure is maintained along the grain boundaries, so this is alpha and this is beta, then it is called coherent. If say some of the boundaries are broken like here, it can be on the alpha or beta phase. If some of these boundaries are broken, then it can be, so this is alpha and this is beta phase, semi-coherent. If all are broken, there will be atomic interaction, there will be bonding, but the crystal structure is, the continuity is not there. If continuity is broken, then if all are broken, then it is not non-coherent. Means all are broken or disturbed. So now the delta GE term, this delta GE term depends on the type of interface, I mean this boundary. So if it is non-coherent, for a non-coherent interface on the boundary, delta G is given as 6 mu epsilon square E C by A. E C by A is a constant. E C by a constant. That depends on C by A ratio. So what this author did, this Carter and this colleague, which they are both, they consider the beta phase to be 3D image cell. Ellipsoid of revolution. So 3D ellipsoid revolution, which is given by x square by h square plus y square by h square plus b square by c square and AC are semi-axis of revolution. Semi-axis of revolution. So these are the semi-axis of revolution. So what is the benefit of using this kind of relationship? If C by A is very less than A, then the 3D left side of revolution will have a shape, disc-like shape. It will be disc-like shape. If this is C is less than A. If C is very greater than A, then you will have a needle-like shape. If C equal to A, then you have a sphere, spherical shape. So by this simple equation, they can describe all different types of shape by considering this constant, which is a function of C by A, this ratio. So if you take the ratio which describes the different shapes, now this is how the effect of shape is taken into account in this elastic strain energy term. So this equation, mu is the shear modulus E is the dilatational strain. Or you can say this is a hydrostatic strain. This is what dilatation. This is equal in all the direction. This is a kind of hydrostatic situation, and the strain is volumetric strain actually. Or you can say the radial strain, not if the shape is a sphere. Otherwise, we can call it Indian dilatational strain. So, shear modulus, dilatational strain, and this is a constant. This constant E, they further gave this E, which is C by A, it varies with C by A ratio from 0 to different values. Say if it is 1, if it is 2, so it goes like this, then falls little bit down, it goes like this. So here when it is close to 0, that means in this region the shape is a disc-like shape. Here you have a sphere, here you have needle-like shape. So this spherical shape, this constant is having this is maximum when the shape is spherical. That means what? When you have a spherical beta phase, nucleates inside the alpha phase, the strain energy will be the maximum because this constant is maximum. But what we know that if you see the surface free energy, the spherical shape always has the minimum surface energy. If you see in nature, if you have a droplet, water droplet or any liquid droplet, by nature they take a spherical shape because they want to reduce the surface energy, minimize the surface of the total energy. But here we see that if the shape is spherical, then because of this term, the strain energy will be maximum. So there will be a competition. So in some cases, to reduce the overall energy, the system can achieve a shape which is not spherical. So spherical shape will not be favored, and because the system will try to reduce the energy. So there will be competition. So what will be the shape? It will depend on the total energy. Ultimately, the objective will be the system will be trying to reduce the overall energy. So we are not going into that full analysis what shape the system will assume in order to reduce the total energy. But you see, spherical shape has the maximum energy. But if you see the disc has the lower strain energy. So disc has the lower strain energy, but the surface free energy would be very high. It is very intuitive. The disc will have very high surface free energy. Generally, graphite in iron carbon alloy is available in different forms. Flakes is one form. So this tells you why graphite prefers to have a flakes form. So this is one of the reasons, or this is one of the ways that we can explain that flakes can have a very good effect in order to reduce the overall energy of the system. So this is how sometimes we get spherical also because it depends on the total energy term. This is what you have to remember about this non-coherent interface. Now if you consider a coherent interface, the coherent interface, for coherent interface, the delta G term is given as 2 mu 1 plus mu by 1 minus mu E square. Here you see this is shear modulus this is Parson's ratio, Here you see for coherent interfaces, the energy is independent of the shape. There is no this term shape factor. It is independent of the shape. There are many other forms that you can follow, but these two are the very basic or most important that you should remember. This equation is given for elastically. This is given for elastically homogeneous system. Elastically homogeneous system means mu alpha equal to mu beta. So remember here mu is the shear modulus. We are not considering mu as chemical potential. Earlier we have used this mu as chemical potential. You have to understand. So now if your system is inhomogeneous, this is given for homogeneous. If your system is inhomogeneous, then there will be some variation. So if we plot delta G inhomogeneous by delta G homogeneous, versus C by A ratio. Inhomogeneous means it will be identical irrespective of different shapes from 0 to say 1, 2, 3. So this is if you have a mu alpha is equal to mu beta. That means this is for homogeneous. But if the material alpha and beta, both the stiffness of the material is similar, that means the shear modulus is identical. But if it is not so, it can have a variation like this. It will have a minimum at about 1, or it can have a variation like this. So what it tells you, this is like, and this is given for 3 mu b, 3 mu alpha, this is mu beta is 3 mu alpha. So why I am showing you this curve without going into all the derivations? This is important to know that you can have beta phase inside alpha. Now alpha and beta, the stiffness, the properties can be significantly different or maybe the same. When the properties are similar, then we call it homogeneous system. When they are not similar, we call it inhomogeneous system. For inhomogeneous system, the equations are very complex, which we are not showing here. But these are some results which I just took it from the reference book. If you see, when the beta is stiffer than the alpha phase, this phase is stiffer than the alpha phase, then what happens? The minimum is, the energy is minimum when the C by A ratio is 1. That means when the shape is spherical. When this beta shape will be spherical. If the alpha phase is stiffer than beta, because this stiffness is 3 times of stiffness of beta. So this is steeper than beta phase. Then you see the disc shape has a minimum energy. So this plot very nicely explains that indeed we can expect different shapes of precipitation for the different phases in the matrix, because of this kind of effect of the property as well as the type of interface. The strength and type of interface actually decides what kind of shape you will get. Of course, there are many other factors, but you should remember these very simple things. So this is all I think. This is all what I wanted to discuss about solid to solid phase transformation, the nucleation. So this is what we have discussed in a brief. We have started with the theories of nucleation. Then what are the critical size, critical energy, how this elastic strain energy term affect these two parameters we have discussed. Then we have discussed the effect of undercooling, effect of supercooling, and we have estimated the amount of undercooling, and also we have estimated the amount of superheating required for solidification or the nucleation of solid phase. And then we have discussed about the shape and the interface of the effect of shape and the interface properties on the nucleation, and also the effect of material properties on the nucleation.